Hey algebra folks. We've been covering a lot about how to actually algebraically manipulate quadratic expressions. So I want to actually move us into the direction of thinking of a quadratic expression with another variable and seeing its relationship with our quadratic expression and that other variable in order to make it a function, right? Sometimes there are things in real life that actually move in kind of a quadratic shape, or as we call a parabola. And by understanding how these functions work, we can actually understand a lot about those real life examples. So let's move on and actually learn about some of the specific properties about quadratic functions and the graphs that they create. So for the upcoming lessons, we're going to be focusing on a very special type of function, specifically with quadratics, right? And we're going to focus on a few of its special properties. So the first thing that we're going to focus on is its shape. And quadratics always form this very special shape called parabola. And it typically looks like a U, right? So sometimes it could be an upward U. So this can be upward or downward. And we're going to look at what actually determines whether or not we have an upward U or a downward U. It also has something called a vertex, right? So there's always going to be a highest or lowest point for our parabola. In the example on the right over here, we have our lowest point right over here because there's no point on this function that's lower than this vertex. Similarly, our parabolas actually have symmetry. So that means that we can actually fold it in half and it'll actually fold right on top of itself. And we call the point at which we fold our parabola in half to fold on top of itself the axis of symmetry. And then finally, just like for other functions, we can determine a domain and range. So basically how wide our function goes, our domain, and how high our function goes, our range. So when we have a quadratic function, we have a few special properties, right? As we talked about before, we have a vertex, right? And when we have a vertex, that means that we either have a maximum or minimum, depending on whether the a in our quadratic function is positive or negative. And so we just want to remind ourselves that for quadratic functions or quadratic expressions, our standard form is going to be this ax squared plus bx plus c, where a is your coefficient for your x squared term, right? And so if that coefficient is greater than 0, right, then you're going to have a minimum and your u is going to be facing upward. So basically when your a is positive. When your a is negative, you get a downward facing parabola. And something that's important to note is that your maximum and minimum, your vertex, it's always going to be a coordinate. So whenever you're asked to give a vertex, you must give a coordinate. So you have to give both the x and the y location for where your maximum or minimum is. So let's look through an example of actually finding the vertex on a graph. So looking at this graph on the left, we want to find our vertex. So we want to see whether we have a maximum or minimum. And I actually see that I have my lowest point right over here, right? And so because this is my lowest point on my graph, and this coordinate where my graph is lowest is 0, 1, my vertex is also going to be 0, 1. So let's do a check for understanding. So you can pause the video here for a minute and just work through this problem where you're identifying the coordinate for the vertex, determining whether it's a maximum or minimum, and then actually circling the vertex on the graph. So pause this video for a minute, take a moment to do it for yourself. All right, you tried it out? Let's check your answer. So we want to see, do we have a maximum or minimum on this graph? Do we have a vertex, right? And so when I look at this graph over here, when I look at this curve, I see that the highest point that it reaches is right over here. So I'm actually going to circle that so I can get that last part of my prompt completed. So that's my, my maximum, right? Because I know that this is never going to go higher than that point that I just circled. So my vertex is going to be whatever that coordinate is, right? And so when I look at this coordinate, I see that it's at 2, 1. So my vertex is going to be 2, 1. Let's look at another example, right? So we know how to find the vertex when we're given a graph of a parabola, but sometimes we're not given the graph and we're just given a table instead. typically if we're given a table on our regions, it actually shows us our vertex. They're actually trying to, give you some hints, right? And so we can tell where our vertex is because we have either a highest or lowest point in our f of x values. So when I look for my vertex in a table, I look to see if I have an f of x or y value that's lower or higher than the rest. So when I look at this, I see that 1 is the lowest f of x value that appears in my f of x row. Because this column in my table has the lowest f of x, this column right over here, I know that this column is going to represent my coordinate, right? So I know that my vertex is going to be at 0, 1 because it contains the f of x value that's lowest compared to every other value in the f of x row. Another thing that actually signals to me that this is going to be my lowest value is that I notice that these y values, these f of x values, actually start repeating or bouncing back before and after this value of 1, right? So it went from 10, 5, 2, 1, and then 2, 5, 10 after 1, right? And that makes sense that it should bounce back because it should mimic kind of the shape of what's going on with this graph, right? So because we're a parabola, we're a U, so we know that at that minimum point, we're going to bounce back, okay? So because this is my lowest y value, I know that this is going to be a minimum as well. So let's do a check for understanding, right? Just like how we were analyzing the table in our previous problem or in our previous example, you want to check to see where do you see an f of x value that is lower or higher than the rest of your values. Determine whether that makes it a max or min, and actually circle the vertex on the table. So take a minute to just try this on your own. All right, you tried it on your own? Let's check it together. So when I look at my f of x row, right, I want to see, is there a value that's lower or higher than the rest? And is there a value where before and after that point, it starts bouncing back and repeating values, right? And I see that right over here, when my f of x is 5, my values start bouncing back, right? I go from 50, 25, 10 to 10, 25, 50, and I'm bouncing back at this 5. And 5 is lower than all these other f of x values. So because it's the lowest value, right? I know that this is going to be my minimum. That's going to be my vertex. And so I look at this column, 0, 5, and write that as a coordinate to represent my vertex. So if we know the vertex and whether it's a minimum or maximum, we can actually determine the domain and range of the quadratic, right? And just to refresh your memory, this goes for all functions, right? But for a quadratic function, unless otherwise noted, your domain is your x values, right? And for quadratic specifically, your domain is going to be all values, right? So when I say otherwise noted, they would specifically say something like x is greater than or equal to 0 or something like that. But then for the most part, in most questions, they won't give you that restriction. So for the most part, your domain is just going to be all values, and you can actually just represent it in interval notation using negative infinity to infinity. For your range for a quadratic, right, unless otherwise noted again, right, your range is going to be one of two different templates, right? So if your vertex is going to be a minimum, then your range is going to be the y value of your vertex, comma, infinity, right? And then you would actually make this into a bracket because you're going to include that y value. If your vertex is a minimum, then your range is going to be negative infinity to the y value of your vertex. And once again, that's going to be a square bracket because you're including that y value. So let's look at an example about how to actually do this, right? So using the example from example 1, right, the same function, I know that my vertex was at 0, 1. So let me just circle that again just so that that's super clear. So my domain, because it wasn't otherwise noted, is going to be all real values. And I know, once again, I can represent this in interval notation as parentheses negative infinity to positive infinity. So because my vertex was a minimum, I know that I'm going to use this template, my y value, comma, infinity, right? And so my y value for my vertex is actually 1, so it's going to be 1, comma, positive infinity. And I want to make sure that this is actually a curly bracket, not a parentheses like this, okay? So using the same graph from example 2, right, you want to, once again, identify your vertex, determine whether it's a maximum or minimum, and then based on that information, determine your domain and range. So take a minute to actually just try this on your own. All right, you tried it on your own? Ready to check your work? Let's check it together. So based on this example 2, right, we said that our vertex was right over here and that the vertex coordinate was 2, 1. And we said that that was a maximum because there was no other point on this graph that was higher than that vertex point, that maximum point right over there. So it wasn't otherwise noted that we were restricting our domain in any kind of way. So we can once again say that our domain is all real values. Oh, and we also have a maximum for our vertex. So this is all real values, and we can write it in interval notation using negative infinity to positive infinity. And our range, because we're a maximum, right? We know that our range is going to follow the template, parentheses, negative infinity, comma, your y value from your vertex, and close bracket, right? And so the y value from my vertex is actually going to be 1. So I'm just going to substitute that value in right over there. And so that's going to be my range. So when we have quadratic functions, we also have another very special property. As we mentioned on one of the earlier slides, right, we have symmetry within this. And you're going to cover how to actually find the axis of symmetry algebraically in lesson 9. But for assignments 7, 8, you just need to know how to find it graphically, right? So if you draw a vertical line going down the x-coordinate of your vertex, then you found your axis of symmetry, right? It's just going to be that x value for your vertex. And so your axis of symmetry tells you that if you fold your graph in half at that line, your graphs should fall on top of each other perfectly. And so if you've actually printed out these notes, you can actually try this out on your paper where you're just folding your paper right down this line and actually seeing that this curve and this curve should fall directly on top of each other. So in lesson 9 and 10, we're actually going to go over the formula for finding the axis of symmetry. So let me just label that we're going to be covering this in lessons 9 and 10. But for now, we just need to know how to find it graphically. So let's work through an example of where we're actually finding the axis of symmetry on a graph, right? So once again, this is our same graph from example 1. We've identified the vertex. We said that our vertex was 0, 1, and we've circled it. And so what I want to do is actually just draw a vertical line going down my vertex, right? And so this vertical line represents that axis of symmetry. And I know that the equation for my axis of symmetry is going to be x equals whatever the x-coordinate is for my vertex, which was 0. So my axis of symmetry for this graph is going to be x equals 0. Let's do a check for understanding. You're still working with the same graph from example 2, right? You want to, once again, find your vertex, draw a line straight through that vertex, and then write your axis of symmetry equation using x equals the x-coordinate for your vertex. So take a minute, try this on your own. All right, try it on your own. Ready to check your answer? Let's do it together. So in example 2 and in other examples where we use this graph, right, this was our vertex because this is our highest point. And what I actually want to do in order to draw my axis of symmetry, I'm just going to draw a dotted line going down this vertex. So I've drawn my axis of symmetry on this graph, right? And my axis of symmetry is always going to follow the equation x equals, because it's a vertical line, and it's going to equal the x-coordinate for my vertex. Now I said that my vertex over here was 2, 1, and so the x-coordinate for my vertex is 2. So my axis of symmetry is going to be x equals 2. So when we have a quadratic, we have a vertex and an axis of symmetry. What else do we have, right? And so it turns out we can actually find out a lot about the quadratics that we have just based on the equation alone. And we can actually predict what the parabolas or the graphs are going to look like, right? So when we are given a quadratic equation, right, not all quadratics or parabolas are going to look the same. So when we think back to our standard form of our quadratic function, we have an a coefficient, right, which is the coefficient for our x squared term. And it changes if our u is upward or downward, right? Like how we discussed in the beginning. And it also determines whether we're going to be a skinny parabola or a wide parabola. Our C term, which is another part of our quadratic that we focus on in Algebra 1, is our constant in our quadratic function. And it determines our y-intercept, or when our graph crosses the y-axis. So let's look at a few examples of how changing some of these can actually just drastically manipulate the way our graph looks. So if you look at the top left graph, this is our standard quadratic where we have a y-intercept of 0 because we see that our graph is crossing the y-axis at 0, right? And there's no shift in terms of whether it's flipped upside down or skinny or narrow, right? So it's our standard parabola where our a equals 1 because our coefficient for our x squared term is 1, right? So because our a is 1, a is positive, right? So our parabola is going to be opening upward, all right? When we look at y equals 1/2 x squared, we change the coefficient, right? We change the coefficient to be less than 1, but still greater than 0. So we know that it's still going to be a positive value, so it should still be facing upward. But because it's less than 1, we're actually going to be wider. So whenever our a is a fraction between, or our absolute value of a, I should be more specific, our absolute value of a is a fraction between 0 and 1, we actually are widening our function. When our function has an a that is greater than 1, or an absolute value of a that's greater than 1, we actually become narrower. So when we actually compare the shape of this graph right over here, y equals 2x squared, and this graph of our standard parabola, y equals x squared, we notice that the y equals 2x squared is a little bit narrower, right? And then finally, when our a is negative, just like how we saw before, our parabola is actually going to be facing downward, right? So if our a is less than 0, then we're going to be downward. So let's do a check for understanding for how a actually affects our parabola. So you're given these three functions, right? F of x equals negative 13x squared, f of x equals 1/2 x squared, and f of x equals negative x squared. What you're going to do is arrange them from widest to narrowest. And I want you to really just focus on the fact that when you're determining width, like whether it's wide or narrow, you're looking at the absolute value of a. So take a minute to just actually figure out which of these is going to be the widest, second widest, and narrowest function. All right, you put them in order. Let's check if you're correct, right? So like I said right before you started the problem on your own, you want to actually just look at the absolute value of a, as we saw in our previous example, where we saw that the absolute value of a determined how wide or narrow our function was. And so just to remind ourselves, right, if the absolute value of a is between 0 and 1, we're becoming wider. When our absolute value of a is greater than 1, we become narrower. Now, we're not looking at whether it's upward or downward because that's not what the question's asking for. We're just looking to arrange our graphs from widest to narrowest. So what I want to do is actually just determine what my a is and then my absolute value of a for each function. So for my first function, my a is negative 13. Therefore, my absolute value of negative 13 is going to be positive 13. For my second function, my a is 1/2, and so the absolute value of a is also 1/2. And then finally, for my last function, f of x equals negative x squared, my a is actually negative 1, so my absolute value of negative 1, or a, is going to be positive 1. And so these are the values that I'm ordering from widest to narrowest, right? And so my widest is going to be whichever value I have that's between 0 and 1, or whichever is the lowest value that I have. And so out of these three values, 1/2 is my lowest, or it's between 0 and 1, right? So f of x equals 1/2 x squared is going to be my widest function. My second widest is going to be my second highest number, which is 1, right? And I see that 1 corresponds to f of x equals negative x squared. So this is going to be my second widest function. And my narrowest function is going to be my a value, my absolute a value that's largest, and that's going to be 13, which corresponds to my first function that I have there, which is f of x equals negative 13x squared. So we covered the basic properties of quadratic functions, and this video is actually enough to carry you through assignments 7 and 8. So take a minute to just review the examples that we covered in these notes. And if you have any questions, remember to just reach out via email or Google Voice. So good luck with assignments 7 and 8. I'll see you for the next set of notes, 9 and 10.